Hi, I'm Jared Erb.
And I'm Nadav Shaibe.
We are graduate students working with Professor Stephen Anlage, and today we are going to be showing you that using a system with multiple electronically tunable parameters, it is possible to create a singularity on demand at any frequency of interest, as long as it's within the tunability range of your system.
Scattering singularities occur when a scattering process, such as reflection or transmission, exhibits total cancellation due to wave interference. Examples of scattering singularities include reflection zero singularities, where none of the energy injected into one port of a system returns to the same port. A transmission zero singularity is where none of the energy injected into one port of a system comes out of a separate port. Coherent perfect absorption occurs when energy injected into multiple ports simultaneously gets completely absorbed within the system. No energy is reflected or transmitted. These singularities have applications in efficient communication between devices, power transfer, filtering, and in detection, as they are sensitive to system parameters. We only explained a few singularities here, but there are numerous other scattering singularities that are interesting and can be created on demand using an optimizer. We will be demonstrating this later in the video.
The system we are using today is a quasi two-dimensional quarter bow tie billiard with 3 tunable metasurfaces along the walls of the billiard. The metasurfaces are controlled by a triple-channel DC power supply, and a vector network analyzer is connected to the billiard through coaxial cables connected to 2 ports near the middle of the billiard. The vector network analyzer measures the scattering matrix, which in our case is a 2x2 matrix because we have 2 ports. The scattering matrix relates the ingoing waves at each port of a system to the outgoing reflected or transmitted waves at each port. For example, the element S21 is the proportion of the signal transmitted from port 1 to port 2, and S11 is the proportion of the signal that left port 1 and was reflected back to port 1. Singularities appear as zeros of the scattering matrix. For example, when S21 is identically 0, that is a transmission zero singularity. This is our physical setup. You can see that our VNA is connected to our quarter bow tie billiard through these blue coaxial cables, which are calibrated out so they don't affect our measurement. You can't see the metasurfaces because the billiard is closed, but these thin insulating cables are connected to the power supply, which changes the voltage on them, and that is how we perturb our system.
In order to create a singularity on demand, first we need to choose which singularity we want, then the arbitrary frequency of interest, such as, let's say, our favorite 10-digit number. For this example, we will demonstrate a transmission zero singularity, so we want to minimize the transmission scattering parameter S21. We use MATLAB to electronically control the VNA and the power supply. Then we use an optimizer pre-built in MATLAB to vary the applied biases to the metasurfaces through the power supply and measure the scattering matrix each time the applied biases change. After setting our frequency and singularity choice in the MATLAB code, we can begin the optimization process. For our setup, the first 20 samples have random applied biases so that the optimizer can explore a wide range of the available parameter space. Then after that, the optimizer begins the process of creating the singularity. The optimization process isn't guaranteed to work every time, and it might need to be run a few times before the singularity is created, but the more tunable parameters you have, the more likely the optimization will work, and generally the faster the optimizer will create the singularity. Of course, we'll never truly reach 0, but at least for us, anything below 10 to the minus 4 is sufficiently close to 0, and there we consider the singularity as being created. For this optimizer in particular, once it can no longer improve the objective function, it will restart the 20 random initial samples and try optimizing again at a different spot in parameter space. In this case, we see that the second try did find a value closer to 0.
As we just saw, by having tunable metasurfaces inside our billiard, we could create a scattering singularity at any arbitrary frequency that we want.
We only showed a transmission zero singularity. This works for just about all scattering singularities, including reflection zeros, determine S zeros for CPA, scattering matrix exception points, etc. Thank you very much.
Thank you for watching.